Our next speaker is Jeremias from UCL, and he'll tell us about predictively oriented posteriors.
Thanks very much. Okay, so, there we go. There we go. Okay, all good. Is there like a contact problem? I think seems all right. Okay. Anyways, thank you very much. I have some good news for myself and some bad news for myself. The bad news is I'm standing between you and lunch, but the good news is that it's English food, so perhaps you will be more forgiving. Yes, so this is some ongoing work, so I'm very open and in fact enthusiastic about any criticism you can levy and throw my way. I'm also a big fan of being interrupted, so if you find anything that doesn't make sense, please don't wait until the end of the talk, and if I don't see you, raise your hand. In fact, just don't raise your hand, just shout in between. I'm very happy to have a spirited debate in the middle of the talk. Okay, so this work obviously relates in some sense to Bayesian uncertainty. And so I think it's important that we just set some bases. So when we talk about Bayesian uncertainty, obviously we'll know what Bayes' rule is. I'm not going to contest that Bayes' rule is a mathematical truth. A lot of my work, however, has contested and has focused on the translation of Bayes' rule into an epistemological principle that allows you to learn from data. What that means is, you can write down a conditional and an unconditional, but in practice you're forced to convert those mathematical abstractions into a model you can actually fit in your data. The moment you do that, you arrive at the Bayes posterior, and it has lots of elegant properties, but it also has lots of problems that we'll see later. Why do people like the Bayes posterior to start with? Let's start with the good things. So there are a couple of really big advantages of doing this, and one of the most obvious ones is that you average over models, and this is what people will often advertise this as. It's like you do not commit to a singular hypothesis in your hypothesis class or parameter in your parameter space, however way you want to phrase it. And as an immediate payoff of this, you also quantify your uncertainty in the form of a probability measure on that parameter space. This prior, which the frequentists hate, also allow you to push your inferences in a particular direction if you have a belief that is preconceived that in a particular region of the parameter space is, or are values of the parameters that you assume will induce good predictives or parameter inferences, etc. So you can include your prior knowledge if you have any. And in terms of the predictive, which is what we shall discuss today, there are actually some really strong optimality guarantees from dating back all the way to the 70s. Specifically, you can show that the Bayes posterior predictive is optimal, provided your likelihood function is correct in the sense that it can recover the true data joining process, and provided that your prior distribution indeed describes how the parameter is sampled in the natural world. Okay, just to give a short GIF, that sort of summarizes for me what Bayesian inference is all about, and one of the big success stories of Bayesian inference specifically in machine learning is the Gaussian process. So you can see here you have some kind of latent function from which you draw observations. You have a subjective notion of uncertainty, which is your red region, and the red region collapses around the truth as more data is observed. Everything is beautiful. In reality, things are a bit more complicated, and that relates to the assumptions you need to impose when you run a Bayesian analysis. And the first and often most problematic assumption you actually have to make is that in order for the uncertainties that you get out of this procedure to have the interpretation you want to attach to them, you require your model to be correctly specified, which means that in your parameter space there lives a theta star which recovers your data generating process. Why is this so important? It's so important because you specify your prior on the, well, if you're really going with Bayesian decision theory, which classically is the motivation for being a Bayesian, you're really trying to cast a prior belief about the true state of the world, at least as it pertains to the data you're going to observe, before seeing the data. And this first assumption justifies you in putting that prior over the parameter space, because it gives you a way of channeling the truth of the world entirely onto the parameter space. Okay, so this is quite an essential assumption. And the second assumption says that you are really capable of writing down your prior beliefs about the world in form of a probability distribution. Okay, so this is a big topic in classical Bayesian statistics and often called prior elicitation. You kind of need to get people to actually formulate what they believe in form of a distribution, which actually is also quite tricky in practice. And the third assumption that I think everybody is familiar with is actually that you can invert these probabilities and you can compute the base posterior in practice. Otherwise, what you're doing might be interesting and it might be relevant computationally in 200 years, but it's possibly, not the most interesting thing you could be doing. So if you want your inferences to be relevant in the real world, you need to ensure that your posterior actually can be computed in a finite amount of time. The chief problem, especially in the sort of machine learning applications that I work on, is that these assumptions are actually quite fragile. And so now I'm going to use a word that will make Sonia angry. But because these things are quite fragile, people have started designing methods that I have started calling post-Bayesian methods. Let me explain what I mean by that. A post-Bayesian method to me is any method that deviates from Bayes' rule as the guiding epistemological principle but seeks to retain the benefits of Bayesian analysis. And I will refer to them as post-Bayesian methods, but we can argue over lunch. Okay, and so these are some of the solutions people have come up with to tackle this problem. And the way I like to introduce them is by creating this hypothetical set of possible belief updates and showing you the base posterior as one particular element in that set. And to show you some of the failures of base posteriors when some of these assumptions are violated, specifically with relation to their predictives, I'm going to show you this plot here. What am I showing you here? So this is actually a Lotka-Volterra model that we're fitting to some predator-prey relationships, which I'm sorry that this gray line is not very visible, but the real gray line here describes the real predator-prey relationships. The blue line and the red line describe what we fit to things. And you can see these like triangles and little circles. These are the data that we've actually used to construct this base posterior. Then we're integrating out the uncertainty of the base posterior, and we're trying to predict on out of sample. And what you will notice is actually two things. So A, we're way off. Okay, so if you see the gray lines, we're nowhere close to them. But actually, even more alarmingly than that, you can see here in the legend, there's allegedly some sort of gray area that gives you the uncertainty around the predictive. And you will perhaps see that you don't see that in the plot. That's not a plotting error. That's because the posterior has collapsed so dramatically that actually your predictive comes from essentially one parameter value. And this is actually quite a common occurrence in Bayesian inference. Okay, so we can see that this does quite poorly. Our uncertainty collapses, and we don't perform particularly well out of sample. And so people noticed this, early on. I'm not the first to realize this. There's a lot of work from the 2000s, specifically the 2010s, from Peter Grunwald's group, who pitched this idea that they call safe Bayes. What's safe Bayes? Safe Bayes is a slightly larger exploration of this space, where you're essentially saying, I could raise my likelihood to some positive power, and thereby the idea is that you temper the likelihood. So you put more mass in the tails, and hopefully you end up with something that is more robust to this kind of misspecification. Okay, so this is what the safe Bayes approach looks like, and it's trying to get rid of the assumption of model misspecification. Of a well-specified model. So it tries to guard you against model misspecification, and it's specifically aimed at producing better predictives. So when you actually look at one of the follow-up papers, I think it's the Bayesian analysis paper with Tim van Ommen and Peter Grunwald from 2017, they look at one example, which is a misspecified regression paper, where you have 50 regressors, so it's a rather large regression model, and it's a really nice example to demonstrate why these power posteriors or cold posteriors, fractional posteriors, again, they have a million names by now, but why these objects could be interesting for prediction. And what they plot is essentially the kind of predictive risk, in this case it's squared predictive risk, that you attain when fitting to the data based on different methods. And so the two spikes you see here actually come from like a classically Bayesian approach. So one of them is actually just the base posterior predictive. The other one is the predictive based on the maximum a posteriori. So you take the maximum of the density and you plug that in. And as the number of observations grow, it seems to decay slightly, but more importantly than that, you can see that if you choose this lambda carefully, you can actually prevent this sort of pathological excess risk. And that's really the pitch of this paper. The other half of the story, though, is what happens when n grows larger. Because essentially what happens is that these power posteriors don't help you anymore, because the same phenomenon that you saw in the other Lotka-Volterra model example happens here as well, which is that the posterior still collapses. Okay? So eventually you start predicting from a singular point either way. And so these methods are really good for small numbers of samples, and here I say small numbers of samples relative to the number of parameters, right? So here in this chart, you can see I've drawn the dividing line where that ratio is at 6. But in general, they don't really help you out. Eventually, they do the same thing that the base posterior does. And so people were thinking, how can we go beyond this? And one of the ideas that they cooked up is what's sometimes called the Gibbs posterior, the generalized posterior, quasi-posterior, pseudo-posterior. Sava?
Yeah, sorry, just one question. So here you assume that there is no hyperparameter inference for the priors, right? So the things are fully Bayesian or post-Bayesian, but you are not fitting the prior to the data before you actually use it in base.
So for what I'm saying, it doesn't actually matter so much. Once you fix a prior class, this always happens. So as n goes to infinity, you get a phenomenon called posterior concentration, which doesn't depend on the prior as long as it satisfies some regularity conditions and essentially forces you to be concentrated around a point mass. And so this is the phenomenon that's occurring here. So even if you did this, it wouldn't rescue you unless you blow up your prior like as n increases. But then you never, then you don't actually learn anything in the limit.
Okay, but you are talking about the asymptotic regime. Okay.
So actually, yes, but the asymptotic regime is practically relevant in really small sample sizes. I think that's the point of this picture. So this happens basically when the ratio of data points to parameters exceeds 6, which it's not that massive. It's not necessarily what happens in neural networks, but for most other models, this is actually a relevant asymptotic regime. Okay, so people thought, how can we recover? And came up with what are often called Gibbs posteriors, which essentially, just exponentiate a negative loss and use that as what they sometimes call a pseudo likelihood and attempt to rectify problems this way. And so we were hearing a lot about scoring rules earlier. And for example, one of the typical losses you plug into this is actually a scoring rule. So I've written everything here in relation to a parametric model p theta, but you can define losses that don't actually even depend on the parameter of the model anymore. I just find it more instructive for what we're going to do in this talk. Okay, so if we look at the predictors that come out of these Gibbs posteriors, okay, so here I've defined what they look like. You just integrate out this other measure on theta. I mean, the principle is exactly the same. What you find, perhaps unsurprisingly, is that you get the exact same behavior you get from the power posterior. The only thing that changes is the point you concentrate towards. And that point is just this theta n hat here, which minimizes your loss function between the data and your parameter. Okay. And this, for parametric models, this happens at rate square root n, because essentially for Gibbs posteriors, you also get something called the Bernstein-von Mises theorem for Gibbs posteriors, which basically tells you exactly this rate of contraction. It tells you much more. In fact, it tells you that this Gibbs measure will be asymptotically normal, and this happens rather quickly. Again, under regularity conditions. And so what this tells you is that, once again, it won't really help you if your model is misspecified, in the sense that no singular point in your model class is a good description of the data generating process. So your predictive here should also misbehave. And in fact, this bears out in the plot as well. So you can basically not distinguish these two plots here, even though the Gibbs measure that you see, that we used to compute the predictive, is nominally robust. Okay, so it's robust to outliers and robust to misspecification, if you wish. But it doesn't fix the underlying issue because, again, you concentrate to like a singular parameter. Yeah, so this is why you essentially go towards a point mass. And what this also means is quite instructive in what we have to do to fix the underlying issue. What we have to do is we have to design posteriors that do not collapse, that continue to average over multiple elements in our model class if the resulting average gives you a better predictive, and they have to do so even in the limit. Okay, so in order to design these methods, what we'll resort to is a optimization-centric perspective on where posteriors come from. So one way you can think of Gibbs posteriors that I find very instructive is you can write them as a linear functional on the Q that you're looking for, plus a strictly convex regularizer, in this case, the Kuiper-Glaser divergence. So this is basically an application of Donsker-Varadhan's theorem. This is very basic. And this is interesting because you can now generalize this. So embedding this into the larger picture I showed you earlier, you can now think of generalizing the Gibbs posterior by allowing yourself different ways of assessing how well the data fit a particular model or posterior and a different form of regularization. And that's what we're going to do. That's the approach we're going to take in order to design new posteriors. Okay, so this is the Gibbs posterior. how do we actually design these Gibbs posteriors in practice? That's relevant here because A, this is a workshop about prediction, and it turns out to be the case that most of these losses are scoring rules, and B, it'll kind of make it more obvious what we're actually doing with these new posteriors. Okay, so normally the losses here are a scaled version of an empirical average over scoring rules, which I've written as SN here, okay? So we just saw an entire talk on scoring rules, so I don't think I have to explain this. The lambda n basically just ensures that as you get more and more observations and this estimate of your expectation gets better and better, you scale it up higher and higher, so you essentially give more weight to the data you've observed, okay? And by the way, this obviously recovers the base posterior for the log score. Okay, so everything I'm going to tell you goes beyond the log score, but actually the log score, i.e. the base posterior, is recovered as a special case. Okay, so I'm slightly changing notation from here on out. This pi n L will always be with reference to a particular scoring rule, as will the optimization problem that it corresponds to. And so one question we can ask ourselves is, why do we actually target an average over the scoring rule? And the answer to this turns out to be that this basically comes from parameter estimation. We want to find the best parameter. And in particular, we want to find the best parameter. This is classically where these objects come from. We want to find the best parameter under model misspecification, but under a very particular model misspecification, and specifically Hoover robustness. Hoover contamination, I should say. So normally you will, if you look into the literature on Gibbs measures and robustness, what you will find is essentially this scenario. People pitch you this idea. They say, oh, there is a data generating distribution which is contaminated by some bad points, but I have hope to recover because a vast majority of my points actually come from some model that I can still capture with my model class. There's a theta zero, so that if I design my scoring rule correctly, I can recover this, and I can downweight the tails. And so this is the link with the weighted scoring rules I was alluding to earlier. This is essentially how these methods function. They will allow you to downweight these extreme points and just recover what would have happened if you had never seen them. Okay. And there are situations where this is actually quite useful. However, it's inherently a parameter inference problem. It's not a prediction problem. You're still trying to find the parameter. You're trying to find the parameter of a data generating distribution you haven't observed. So you want to exclude essentially some points implicitly rather than explicitly. And so this is why you look at this particular objective. But that's not what we want. We want to perform prediction. And so what that means is we actually have to target the predictive rather than the parameter. And when we are Bayesians or generalized Bayesians or post-Bayesians, we average over the measure that we find on the parameter. And so what we should really be looking at is the score with respect to the implied predictive. Okay. So when I write this out here, obviously this is a bit ludicrous in terms of the computation, but if I get to it in the end, I'll show you how you can actually make this work. You have an implied predictive here, and that's now the object that you are scoring, not the model itself. And these are the objects that we're calling predictively oriented posteriors, or pro-posteriors. And that's what I'm going to talk about for the remaining 10 minutes or so. And specifically, I'll try to show you some of the theoretical guarantees that we're currently providing. This work isn't published yet, but the results are in. This should come online in the next month or so. So these objects, they don't collapse, and they do actually target the best available average over the model class that you could find. And you can show this explicitly. First, I'll show you just this picture to compare what we saw before. Okay, so perhaps unsurprisingly, you have now rectified the issue we lamented earlier. We do actually get uncertainty because we do not get a model collapse in this case. And yeah, so basically it does what it says on the tin, and everybody's happy. Okay, what actually happens though, this is always the first question you'd ask yourself, what actually happens is the problem I have drawn up doesn't exist. Okay, what if my model is actually well specified? Actually, it turns out that these pro-posteriors behave really nicely in this case. Okay, so I was lamenting through much of this talk how Gibbs posteriors collapse, and that's a bad thing. That is a bad thing if your model is wrong. If your model is right, that's perfect. You don't want any uncertainty. You just want to find like the right model. And actually, this is exactly what happens for these objects as well. So if your P naught corresponds to some P theta star, then actually you get classical posterior concentration results here, in a sense. So to unpack this, basically the 1 over square root n rate is the classical rate you get for a parametric Gibbs posterior as well. And here, the balls that you're considering is kind of the only non-standard thing. The balls you're considering for which the posterior contracts are the balls that are spanned by the discrepancy induced by the score which you have used to construct the posterior. Okay, so it's this DS object. Okay, so that's nice. And then the other part of the equation that we care about is if the model is actually misspecified, does this do better? And in fact, it does, so you can derive under some mild regularity conditions on the nature of the misspecification. There's some cases where this is inequality, but they're very pathological. You need to try really hard to find them. In general, you will do better, unsurprisingly, if you're allowed to average over more points. Okay, and so in general, you will find this result, which is that the pro-posterior predictive is actually a better description of the data generating process than the predictive obtained from a Gibbs posterior. We also have some interesting generalization bounds. And so these are fairly universal in the sense that here they are agnostic to your data generating process, and they're also agnostic to the choice of K. The K is a fictional object. I will introduce shortly where this K comes from. It's just some natural number. But essentially what you can show, unsurprisingly, as with most generalization bounds, is that there is an irreducible error, which will depend on K, and then there's a finite sample error, which will decay in N. We haven't verified this yet, but it should decay at rate square root N. And so for now, I've just written this as delta nk. I don't want to lie to you, but I think it will scale linearly in k, and it will decay at square root n rate. And it has an irreducible error. And to define that irreducible error, you need to define some auxiliary objects first. So imagine you had access to the true data generating process, and you used this score-induced discrepancy to fit a k mixture model to p naught. So you have the ideal mixture model in your model class. And you define the omega and the theta star 1 to k as the result of that fitting procedure. If you do this, then the irreducible error is essentially the remaining part of the distribution you haven't explained. Okay, so it's fairly straightforward. You just look at the best fitting k mixture model over the original model class and p naught as measured by the score that you started the entire procedure with. And that's your irreducible error. Okay. So how should we interpret this sort of fairly terse statement? What it basically tells you, and I'll make this more explicit on the next slide, is that pro-posteriors can approximate any data generating process that is well described by like a finite mixture model. Okay. And it doesn't really matter how many mixture components you need. However, you will need more data for a larger mixture component to work. And so you can actually make this explicit, right? So let's assume that P naught here is actually a mixture of your model class. Then you can show that there is no irreducible error, and you're only ending up with this finite sample error, which once again will normally decay at rate square root n, and will grow at rate k. Okay, so I also spoke about Huber contamination, because people care about this in this literature. So let's assume that your P naught is actually a kind of Huber contamination of a mixture model you could recover exactly. Okay, so we have a mixture model here, which is a fraction 1 minus epsilon of your data. And then an epsilon fraction of the data is also from something that we possibly cannot describe very well. Again, we're completely agnostic to the nature of C, this contamination model. Then what you find is a composition, again, into finite sample error and irreducible error, but now the irreducible error scales in epsilon. And so in particular, the finite sample error, so the thing that grows linearly in k but decays at square root n, that will be a fraction 1 minus epsilon of your generalization error, and a fraction epsilon of your error comes from, of course, the remaining part you once again cannot explain. So it's now the discrepancy between that idealized mixture model and the contamination. So this could be large. It depends on where your contamination occurs. It depends on what kind of score you've chosen. And of course, this entire generalization bound is always relative to the score. Okay, so whether or not it's meaningful depends on how you've designed your score and what you want from your distribution, but it's always there for you. And yeah, what this basically tells you in sort of classical statistical robustness terms is that your pro-posteriors are actually Huber robust, or robust in a Huber sense, against contamination, against arbitrary finite mixture models of your original model class. Okay, great. So we've derived this object, which is theoretically nice and conceptually nice, but can we compute it? Because this does not have an analytic form in general. I can write this down, I can show you that it has a unique minimizer, and I can show you nice properties, but can I compute it? Because otherwise, you remember assumption 3 from the first slide, assumption 3 said, unless I can compute it, it's not relevant. So I'm sweating bullets, but hopefully I can convince you that you can actually compute this object. So what turns out to be the case for a lot of scoring rules is that you can actually rewrite this object as what I've started calling a k-linear object, but the better way to phrase it is an expectation over the product measure of order k. So for example, the maximum mean discrepancy or kernel scores, as well as the CRPS, actually you can rewrite as a linear form where this k is 2. And even if this isn't the case, you can construct approximations that, actually fairly straightforwardly, fairly brute force approximations that, when I say brute force, I mean more they always exist, not that they're very hard computationally. You can construct these approximations and the results I've shown you will still hold. And so if this thing is linear in the product measure, then you can actually do two things to perform inference or to compute this. The first of them is you can see this entire object as a KL projection. It's a really funky KL projection, so we kind of have an implicitly defined Gibbs measure now, but the Gibbs measure is on the wrong space. The Gibbs measure is on the space theta k, but we actually don't care about this auxiliary space. We only want one dimension. So you actually project a non-symmetric Gibbs measure. I mean, if it's symmetric, this projection is easy, but it's generally not symmetric. You project that down onto a singular space. There's one way you can do this. And there's a second way, which is actually sampling. And so to explain that a little bit, you essentially can perform a version of Wasserstein gradient descent on this objective because you have something that's linear and convex. It's linear in not the ideal space, but we actually have a version of this that we derived originally for something completely different in 2023. And then more recently, we reused this for something. And in this forthcoming work, we realized actually this Wasserstein gradient flow construction is much more broadly applicable. Okay, when I say Wasserstein gradient flow, what do I actually mean? I essentially mean an interacting particle system. Okay, so this approximation requires that you have a growing number of particles. So if you're familiar with, for example, the literature on sequential Monte Carlo, you know the nitty-gritty here. It's quite difficult to get this to work well, but you can make this work. Okay, so what does a sampler look like? It's essentially an SDE, and you have an interacting particle system equation. There's a reason I haven't put this here, because it's very nasty, and I don't think there's much merit in explaining it. So I will skip through these slides. But it looks horrible, but it's actually very simple. And so rather than spending time dragging you through the SDE, I'm just going to summarize and leave some time for questions and lunch. So what we started with is that there are certain assumptions baked into Bayesian procedures that cause you to produce really brittle predictive distributions. And that, in fact, when your model is misspecified, you have really poor performances. You also weren't able to fix this with power posteriors or Gibbs measures. And the reason for both was that in either case, you're still trying to do parameter inference. You're still trying to find the best fitting parameter in the class of models. And that will fail if you're looking for the best predictive. And so if you care about the predictive instead, you could just swap the order. And rather than getting the predictive as a consequence of parameter uncertainty, you could get parameter uncertainty as a consequence of the predictive. And this is exactly what the pro posterior implements. And it implements a funky sort of best of from both parameter estimation and density estimation. It has some strong theoretical performance guarantees specifically on the predictive that you get out of it. And you can make the computation feasible, even though there are smarter people than me that should probably look onto the computation side of things. So I'm hoping to pitch this work to some of my Bayesian colleagues who do nothing but MCMC. And I'm sure you can do some intelligent stuff in that. Anyways, sorry, I'll leave it there. Thank you very much for your attention.
Time for one quick question.
Yeah, thanks. Very interesting talk. My question is, so I basically kind of understand the tree, but I don't understand the intuition why it helps to fix the uncertainties. So, yeah.
You don't, sorry, what do you mean? You don't understand why it helps to fix the uncertainty?
You have plots on the left, you have bad uncertainty. On the right,
yep.
Good. Your method improved. But why putting this predictive posterior inside helps to improve that?
Why it helps?
Yeah.
Yes, okay, sorry. So this is essentially, I probably didn't explain that as well as I could have. So this essentially is down to this result here. So when you use a general Gibbs measure, which includes a base posterior as a special case for the log score, under mild regularity conditions, but even if they are violated, this basically happens in some way or another, you collapse towards a point mass. So your posterior very quickly converges to this, which means that the predictive that this implies actually also is just a plug-in estimator. So it's like you're finding the best theta hat, and then you plug that into your predictive. Okay. So that's kind of what you're steering towards if you use a Gibbs measure based posterior. In contrast with these QL methods, what we saw in the generalization bounds I showed you is kind of the qualitative behavior of these things, right? So I think this is probably the most instructive. So let's assume there is a mixture over your model class that would be a better description of the data generating distribution. Then actually you recover that exactly in the limit. So you don't collapse to a singular point, you collapse to a mixture over points. And whenever a mixture over points in your model class is better, you do better than the base posterior. So this is kind of the qualitative behavior of these plots.
Well, it was just a comment, maybe we can talk later, but when we were talking, I was thinking since the beginning, well, why don't using a non-parametric prior? If one is uncertain about the model, at least that's my, I'm used to, well, I say I'm certain about the model and I put a prior with a larger support, for example, a mixture model, no? Because you want to keep something of the parametric model, so a mixture. And it's very nice, I like it. But well, it's just for perhaps a comment. I understand it's a different approach and you make specific what is the kind of robustness you get. So it's very good. Well, maybe.
So my answer to that was, so I think that relates to the larger point of why don't you just do density estimation directly, right? I think that would be a valid competitor if all you care about is the predictive. So I would say two things to that. So A, with density estimation, you often get much worse rates than this. It depends a bit on your density estimator. But more importantly for me, actually, is often we're in this in-between setting where we don't want to commit to parameter inference because we don't believe there's a best parameter, but we also don't want to commit to density estimation because we still think these parameters are interpretable and maybe some uncertainty over them gives us something. So if you think of a lot of scientific applications, you come up with a model that you know is a bit crap, but you still care about that parameter because everybody else in the literature cares about that parameter. And so I think it's kind of a third way between parameter inference and density estimation. And when you do Bayesian and parametrics, I think you're more in the density estimation landscape. Yeah, it depends, I agree.
Thank you.
Very quick.
Okay, just connected to this, do these results also apply to neural networks, deep neural networks, where your model class is really still parametric, but very rich and has universal approximation properties?
So,
because this is very interesting from a machine learning point of view, where people are now working on these Bayesian versions of neural network, deep Bayesian networks, and so on.
So yeah, so there's actually some prior work that we were partially inspired by, which looks at the log score specifically. So there's a paper by Andres Massagosa from 2020 at NeurIPS, and there's a paper by Morningstar and Alemi 2 years later, I think, at UAI, who do exactly what you're describing. So the problem is, in both papers, so they do look at the setting, the problem is you need a condition on these loss functions, which I have absorbed into under mild regularity conditions. What you classically need is a kind of Höfting assumption on the loss. And so that restricts you. So a lot of the results I've shown you, I think spiritually they should still hold. But fundamentally the problem with neural networks is that we often have very bad understanding of the kind of properties of the induced loss functions. So I think in both, if you're interested in this specific question, I would point you to these two papers, because they do look at this and it performs much better in practice, even when the loss violates these fairly standard conditions. So I should mention a lot of these bounds come from pack-Bayes theory. So you kind of tie to the assumptions people make in pack-Bayes. And so I think if you're really rigid, no, this doesn't extend. But if you think of this as a spiritual truth that might ascend beyond the narrow confines of the assumptions you have imposed, then I think very much yes. And so it depends a bit on how happy you are to go above the assumptions you had to impose. For us, it was important that we find a set of minimal assumptions that makes this true. And actually, the assumptions are fairly narrow. It's essentially convexity of the score. It needs to be proper. You need a prior mass condition for the concentration to happen. And you need the Höfting assumption on the loss. And that's really it. Like, it's very minimal. It's not very construed. But that assumption, I think, would break some applications in neural networks, at least.
Okay, let's go for lunch. Let's thank Jeremy.